When you hear about Duchenne muscular dystrophy, your mind probably jumps straight to the genetics, the missing dystrophin protein, right? But what if that's just the start of the story? What if the real crisis is a complete breakdown of the cell's most basic maintenance? We're going to dive into this, because new research is showing that a failure in the cellular housekeeping is a massive part of the disease. And here's the really cool part. Figuring out how to fix that could open up a whole new playbook for how we fight this.
And just to set the stage, let's talk about why this is so urgent. Duchenne muscular dystrophy, or DMD, affects roughly 1 in every 3,500 boys born across the globe. That's not just a statistic. For thousands of families, it's a daily reality, and it's why the search for better treatments is an absolute race against time.
All right, so here's our game plan for today. First, we'll do a quick rundown of DMD itself. Then, we're going to introduce the cell's incredible recycling system. After that, we'll see exactly how that system crashes in DMD, explore the amazing new ideas scientists have for rebooting it, and finally, take a look at what the future holds. Okay, let's kick things off at square one, the genetic problem that gets this whole domino effect started.
So, what is DMD at its core? It's a genetic disorder. It's X-linked, which is why it almost always affects boys. The fundamental issue is a flaw in the gene that's supposed to make a protein called dystrophin. You can think of dystrophin as the crucial shock absorber and structural support for muscle cells. Without it, muscles, including the heart, just become incredibly fragile and break down over time.
Let's just trace that initial chain of events. It all starts with that one mistake in the gene. Because of that mistake, the muscle cells can't make the dystrophin protein they need. Now, why is that so bad? Well, without that shock absorber, the cell's outer wall becomes super fragile. It tears easily, and that allows a flood of calcium to rush inside the cell. For the inner workings of a cell, that much calcium is basically toxic, and it sets off a whole cascade of damage.
But that initial damage, believe it or not, that's only half the battle. To really get the full picture, we need to zoom way in, deep inside the cell, and meet one of its most important unsung heroes. Let's talk about the cell's master housekeeper, a process called autophagy.
Honestly, the best way to picture autophagy is to imagine a dedicated 24/7 cleaning crew that lives inside every single one of your cells. Its job is to constantly patrol, find anything that's old, broken, or toxic, like worn-out machinery or clumps of garbage, and haul it off to be recycled. It's a non-stop process of tidying up to keep the cell in perfect working order.
So, to put it a bit more scientifically, autophagy is this fundamental process for breaking down and recycling cellular parts. And this isn't just about being meat. It is absolutely critical for survival, especially for cells that work as hard as our muscle fibers do. By clearing out all the junk, autophagy basically maintains quality control and stops the cell from choking on its own toxic waste.
And this, right here, brings us to the heart of the problem we're exploring. In Duchenne muscular dystrophy, this essential housekeeping system doesn't just slow down, it fails. And that's when things go from bad to catastrophic. So how on earth does this amazing system just break? Well, remember that constant damage and that flood of calcium we just talked about? All of that chaos creates a mountain of cellular trash. The cleaning crew is just completely overwhelmed. They can't keep up. And eventually, the entire recycling system just grinds to a halt. This slide just lays it out so clearly, doesn't it? On the left, in a healthy cell, that recycling crew is working like a well-oiled machine. But then you look at the DMD muscle cell on the right, and the system is just blocked. It's a total shutdown. It's like the city's garbage collectors all go on strike at once. The trash piles up in the streets, and that toxic buildup leads to even more inflammation and damage.
And this isn't just a metaphor. We can actually see this traffic jam in the scientific data. Scientists look at these specific markers. So LC3I, you can think of that as the number of trash bags the cell is making to collect the junk. As you can see, in DMD muscle, that number is way down. They aren't even bagging the trash properly. At the same time, P62, which is basically the trash itself, is at super high levels. It's just piling up because the disposal system is completely jammed.
And a failure this big has absolutely devastating consequences. The cell's power plants, the mitochondria, start to fail. Chronic inflammation goes into overdrive. The cell's protein-making factories get all gummed up and stressed out. And maybe worst of all, the muscle loses its ability to repair and regenerate itself. It becomes this vicious, downward spiral where every problem just makes all the others worse.
But, okay, that all sounds pretty bleak, I know. But this is where the story takes a really hopeful turn.
because if a broken system is a key part of the problem, well then rebooting that system could be a huge part of the solution. So let's look at the strategies being developed to do exactly that.
Researchers are basically launching a three-pronged attack to get that cleaning crew back on the job. They're testing drugs that can directly kickstart the process, looking at dietary changes that can naturally encourage it, and even using advanced tools to change which instructions the cell is reading to get the system back in balance.
So a great example is a drug called rapamycin. There's a pathway in our cells called mTOR that kind of acts like a brake on autophagy. Rapamycin works by basically taking the foot off that brake pedal, which gives the cell's cleaning crew the green light to get back to work. And get this, it's not all about high-tech drugs. Sometimes, a potential solution is a lot more fundamental. Studies in preclinical models have found that something as simple as a low-protein diet can do something similar. It also helps take the foot off that mTOR brake, which improves the whole recycling flow and helps reduce muscle scarring.
And then you've got even more advanced stuff, like givinostat. It's called an epigenetic modulator, which is a fancy way of saying it doesn't rewrite your DNA, but it changes which pages of the blueprint the cell is reading. It acts like a master switch to turn on genes that not only ramp up autophagy, but also promote the creation of new, healthy mitochondria. So it's tackling two of the biggest problems at the same time.
So this new way of thinking is incredibly promising, but we're not quite at the finish line yet. Let's be real about the challenges that researchers are tackling right now and what the road ahead looks like.
There are really three big hurdles. First, you need a way to see if your treatment is actually working in real time. Second, this is a delicate balancing act. You need to turn up the cleaning just enough to clear the junk, but not so high that the cell starts destroying healthy parts, which could actually make things worse. And finally, there's the delivery problem. Getting these therapies to all the muscles that need them, not just in the legs, but also the heart and the muscles we use to breathe.
And this quote from the research just nails it. The real goal here isn't to find one magic bullet for one symptom. The key is to get a deeper, systems-level understanding, to see how the missing gene, the calcium overload, and the failed cleaning system are all interconnected pieces of one giant complex puzzle.
And that leaves us with this final powerful thought. Autophagy is one of the oldest, most fundamental survival tools our cells have. By finally understanding its critical role in Duchenne, we might be on the verge of turning that ancient system into our most modern weapon. Could mastering the cell's oldest recycling system be the key to unlocking the future of treating this devastating disease? It's a question filled with an incredible amount of hope, and one that scientists are getting closer to answering every single day.